have 4 slides, but they're shorter. They should be a little bit shorter slides. But we are doing 2 sections, and the content is knowing terminology. So these are words that you need to be able to sort of memorize which one goes with which. And there's 4. Each slide has its own what are called points of concurrency. Okay? And so, again, we'll see how long it takes to go through and explain these. All right, so for these next 2 sections, 6.2 and 6.3, we're going to talk about four points of concurrency, which is a point where 3 specific lines or types of bisectors intersect on a given triangle. Okay? And so the first one is called a circumcenter. Okay? When you look at this, these are called points of concurrency, which just means a point that's shared by multiple elements. And the circumcenter is for all 3 perpendicular bisectors. Okay, and so right here, this point P is called the circumcenter. Okay, and so the markings that you're looking for to designate this is you need to see that you have a line that's perpendicular and a bisector. Okay, so I'm going to show you on this triangle below here. So if we take this given triangle and we find the midpoints of all 3 sides. Okay, so here's one midpoint, here's a second midpoint, here's a third midpoint. Now, obviously, I'm sketching this, so it may not be exact, but these are the markings. So you find the midpoint, and then if you construct a perpendicular through this midpoint, and remember, a perpendicular is perpendicular to, right? So this right here is a perpendicular bisector. If we do the same thing here, perpendicular, and then we do one more. Now, do we need the third one to find where this point of intersection is? Or do we already know? If all 3 of these lines are going to intersect at that point of concurrency, will 2 of them? Yeah, so you don't even really need that third one. We know that right now, the point of concurrency for this is this point right here. Okay, now we can confirm it. Like I said, this is sketched, so no guarantees that it's confirmed. But it would be this perpendicular bisector here. This third one would confirm that we have the right point. Okay, but that we only need the 2 of them to find what that point is. Okay? All right, so that is how you find the circumcenter for this. Now, here's what the circumcenter does. Okay? And so it's this circumcenter theorem, which states that the circumcenter of any triangle is equidistant from each vertex of the triangle. Okay, and so what that means is that if you look at this measure from A to P, B to P, and P to C, these are all the same measures. Okay, these are all exactly the same. So AP is equal to BP, which is equal to CP. Okay, and what that allows you to do, or the whole point between this circumcenter, is it allows you to find a point that's exactly between 3 locations. Okay, which means, like, if you were putting the actual direct usage of this, if you need to put a radio antenna or a cell phone antenna that reaches 3 different cities, if you had a city here, here, and here, the location of that cell tower so that it'll reach all 3 cities with the sort of the equal strength would be this point, this circumcenter. Okay, which means that if you drew a circle with the center at that point, that circle would pass through all 3 vertices of the triangle. Right, so see if you can use the concept of this and what things are the same, right? So this distance here here, and here. These are all the same measures. So I'll use 4 tick marks for that. Okay, those are all radii of what's called a circumscribed circle. Okay, it's also referred to, if you take the reference point of the triangle, that's called an inscribed triangle. So the triangle is inscribed in a circle. The circle is circumscribed about the triangle. Okay, but see if you can answer the questions here on this problem to the right. But you should be able to tell, right? In the question, it tells you this is the circumcenter. You can see right here that these are perpendicular, and you can tell from gauging the looks of these that this is also the midpoint. So you have the perpendicular bisectors. Okay, so when you look at this AG, AG is this distance. Well, all of these radii are the same. And so if you look from G to C is 21, that means G to B is also 21, and G to A is 21. So that's your first answer. Okay, BD, this whole distance here, you see 2 tick marks. That means that BD is also 19. CF is this 3 tick marks, so that means that this is also 20. Just like AF was. AB, this whole length is 2 19s, which is 38. CE is this measure, it's 1 tick mark, so it's equivalent to 14. AC is this whole length here, 2 20s, so that is a total length of 40. ADG, so A to D to G, this angle, this is a perpendicular bisector. Being perpendicular means that that's a 90-degree angle. And then finally, BG, you see right here was also 21. So if you took 2x minus 7 and said that's equivalent to 21, and you solve here, if you add 7 to both sides, divide by 2, you get x is equal to 14, and that's what you are measuring. Okay, and so that's using all of the different properties of the circumcenter, okay, to answer those questions. All right. So we're going to compare this to the other 3, right? There's a total of 4 different points of concurrency. The next one is the intersection of the angle bisectors, and that's called the incenter of all 3 angle bisectors of a triangle. So in this particular case, P is the intersection of the angle bisectors. Okay, so let's look and again kind of see what this looks like. So if you took a triangle and you drew in angle bisectors. So again, I'm just going to buy like kind of the eye test. I'm going to bisect this angle. I'm going to do the same thing here. Again, this angle and this angle are the same, which tells me right now, again, once I find 2 of them, I should be good. That third one should pass through the same point as well. And so if I start from my vertex and I bisect this last angle, it should pass through that same point. That is my incenter. Right, so that is the second point of concurrency that you need to be familiar with. Okay, now the circumcenter is the center of a circle that passes through all the vertices of a triangle. The incenter is going to be the center of a circle that's inscribed within the triangle. So what this means is this point is going to be equidistant from each side of the triangle. Okay, so the circumcenter was equidistant from each vertex. This is going to be equidistant from each side. Okay, and so this is what it's going to look like, or what's going to happen. So that means that this distance, remember distance is a perpendicular measure, is the same as this distance. Oops, I'll use just 2 tick marks for each of these. And it's the same as this. Now again, these are perpendicular measurements, so these are all the same. So if you took that in-center and you drew the same distance here, the same distance here, and the same distance here, what you're going to see is the only way that can happen is if there's a circle that passes or that's contained inside this triangle and is tangent to each of the sides of that triangle. So this is called an inscribed circle. Okay, so now the circle is inscribed in the triangle, whereas before we saw that the triangle was inscribed in the circle. All right, so once again, see if you can use the relationships of having the angle bisectors all intersect at the in-center to answer the questions in the table for this second question, or this next question. And so if you're looking at these measurements, the in-center is the intersection of angle bisectors, so we know that these 2 angles are the same, these 2 angles are the same, these 2 angles are the same. And so there's your angle bisectors. They intersect at this point, T. T is a distance of 11 units from each side, so that means that this will also be 11, and then this distance here also 11. Remember, you could inscribe a circle here where each of those distances is the radius of that circle. Okay, and then this can help us come in and identify our answers here. So if we look at first question, ST, S to T we see is 11. TU here again also 11. So if we take that expression 2x minus 7, set it equal to 11 and solve, add 7 to both sides, and when we do, we wind up seeing that you're looking at 9, divide by 2. Okay, and then finally, P angle PRT, if we look here, P to R to T, oops, right here, this angle is 17. If that's the case, then that means this angle is also 17. So QRT is a measure of 17. And then finally, angle RPQ is 60 degrees. So if this whole thing is 60 degrees, that means each of these is half of 60. So 30, meaning RPT, this angle here, is 30 degrees. Okay, and so that would be your measurement. All right, questions on that? Okay, so that's the first 2, circumcenter and in-center. Okay, there's 2 more that are included here. The next one is called a centroid. Okay, so the actual point of concurrency is called the centroid here. So I'm going to define that first, and then I'll come back and I'll talk about the median. But a centroid is the point of concurrency of all 3 medians of a triangle. Again, right here, point P is called a centroid. And the reason that median is above this is we need to define this, because we haven't specifically said what is a median. And so a median is defined as a segment that connects a midpoint to the opposite vertex. So if you found a midpoint of one side and then you drew a straight line to the opposite vertex, that's called a median. And so if you took all three medians in a triangle and connected them, you would have what's called this centroid. So let's again kind of take a look at this. So the first thing that you would do, just like with the perpendicular bisectors, you find the midpoint. Next, you connect that midpoint directly to the opposite vertex. So if we draw a line from this midpoint to the opposite vertex, that is a median. From this midpoint to the opposite vertex, that is a median. And so once again, if we're looking to define it, we see that this is going to be our centroid right here. And we can confirm that by drawing in the last one. Now notice here that we're probably going to be off just a bit. Okay, but that is where our three medians will intersect. All right, so here's the centroid theorem. This one's a little bit more confusing than the other two that you need to know. All right, so the centroid of a triangle is the following. It's 2/3 of the distance from the vertex to the midpoint. Which means it's going to cut the median, or cuts each median into a ratio of 2:1. All right, so the centroid has a little bit more to it than the others. Okay, the centroid is also the balance point. If you took any triangle and you calculated the centroid, meaning you found the midpoint, drew a line from the midpoint to the vertex, and found where two of those intersect, that's the point where that triangle would balance, like on your finger or on a focal point. Okay, so this is also the center of gravity or the balance point of a triangle. Okay, but the ratio, what happens is that by the definition, or by this theorem right here, it says that 2/3 the distance from the vertex to the midpoint. What that means is that if you took this whole measure right here, if that whole measure was x, then that means that this distance right here is 2/3 of that, 2/3 of x, and this distance here is going to be the remaining 1/3. Okay. Now, that's if they gave you the whole median itself. So it's 2/3 from the vertex to the centroid, and then the remaining 1/3 to the midpoint. Again, I'm gonna zoom in on this as I write that. Okay, so that is that's the information provided in that theorem. Okay, there's a couple other relationships here. Okay, it's a ratio of 2:1. So what that means is if we were given just this portion to the midpoint as, let's call it y, that means that this upper portion is double that. So that's going to be 2y. Okay, and now because it's that 2:1 ratio, what if instead of being given that measure, we were being given the longer of the two? If we called this z, then that means that the portion to the midpoint, if it has a 2:1 ratio, is going to be what fraction of z? Oops, it's kind of hard to see there. It's 1/2 of z. Right, and so that's going to be the relationships that we're looking at. So I'm going to rewrite these here in this triangle below because it's a little bit bigger. And I'm going to use slightly different letters. So if we have this length as x, then the portion up above is double it. If we have this length as y, then the other portion here is going to be 1/2 of y. And finally, if we have this whole length here, which I'll call z, then the portion to the vertex is 2/3 of that z, and the portion to the midpoint is 1/3 of that. And so those are the measurements that you're looking at for this. Right, so using those relationships, see if you can answer the questions on that table. All right, so I'm gonna kind of talk through and show, like, this is sort of how you can take the information given and then apply these three relationships, right? But they're all built on that ratio of 2 to 1. All right, so we know it's a centroid here, and we're told that CD is 12. So if we know that this whole length C to D is 12. Right, so let's take a look at what we know and what we're given here. Okay, so this portion, this length A to G is given as 11. And that means that the portion to the midpoint is going to be what fraction of that? It's a 2 to 1 ratio, so that means 11 is twice the measure of GE, which means GE is half the measure of 11. So 11 halves is what we would get for that. Okay, now, if we know that this whole length from D to C, or so not from here, let me remark that. So it's this length D to C, that whole length is 12. That means that this upper portion is 2/3 of it, the lower portion, the smaller portion is 1/3 of it. So what's 1/3 of 12? 4, and then this upper portion is double 4, right? It's a 2 to 1 ratio, so what's double 4? 8. And that's probably the easier way to sort of use that. And now you have the information you need, so you can find your answers. Now D, F, and E, these are all midpoints, right? So that means if AD is 6, that means that BD is also 6. AE here is this 11 plus 11 halves. If you think of that, 11 halves is 5.5, so 11 plus 5.5 is 16.5. AB, this length here is the whole length, 6 and 6 added together, so 12. CG, C to G, we saw was 8. E to G here is 11 halves, or 5.5. And then finally, DG is this length from here to here, which we calculated as 1/3 of 12, or 4. And so those are the measurements that you're looking at for the centroid. All right, the final point of concurrency is one that there's not really, we're not going to do any calculations with it. It's called the orthocenter. And the orthocenter, again, I'll go in and define orthocenter first, and then I'll come back and define the term that we use to define it. But orthocenter is also the last point of concurrency that we're looking at of all three altitudes of a triangle. And so here point G is the orthocenter. Okay, altitudes are heights, okay, or perpendicular segments. Okay, so by definition, the altitude is the perpendicular from the vertex to the opposite base. Okay, or it's another way to call it the height. Okay, altitude can fall inside of a triangle, but it might fall outside, like you see here on the one to the right. This altitude falls outside of the actual triangle, whereas here in this example to the left, the altitude falls inside. So it can be either. Okay, and if we come down here to this triangle, the way that you would find the orthocenter is you would find the altitude from each vertex. So if we took each vertex, found a perpendicular to the base. Again, once you find two of them, you'll have your orthocenter. The third one, if you found this third one, it would just confirm that you have the right point. And so that's the intersection of all three altitudes. And again, the question that you're going to see for this won't have any calculations of numbers. It'll just be these relationships right here. So see if you can answer this final question, and then I'll open up your homework and give you a chance to work. So be really careful with this figure and make sure that you are reading the triangle name carefully. Okay, so notice that we're looking at triangle GEM here. So triangle from G to E to M. All right, so this is the triangle that we're identifying. Okay. So it asks, choose all segments that are altitudes. Well, if you go to a vertex of this triangle and you find what is the perpendicular to the opposite base. So we see right here that DE is a correct answer, right? All right, let's do the same thing from each of the other vertices. Okay, so if we look at point G, if we want to find the perpendicular from point G to the opposite base, what we would have to do is we'd have to extend this base out, and we find the perpendicular. So is GH an altitude here? Yes. So GH is also a correct answer. And what if we look for point M? So to find the altitude of M, we need to extend the opposite base and then find the altitude. Do we have that marked on this? No. So you only have two altitudes shown here. Okay? So again, kind of be careful, make sure that you look at what triangle is being identified. Okay, now it says choose all of them that are medians. A median connects a vertex to the opposite midpoint. So D here is given us a midpoint. D to the opposite vertex E, that is our one median in this example.